Hi everyone, I hope you are doing great and I hope everything is fine with you. We already had our first lecture last week, so this is our second lecture, week 2. We will be discussing operating system structures in this lecture, and this is chapter 2 of your book. I have not received any questions from any of you, so I hope everything is clear. If you have any questions regarding lecture number 1 or exercises or anything else regarding course flow and so on, please drop me an email. My email address is over here, razi.iqbal@ufv.ca. So please drop me an email and I will try to get back to you within 24 hours. So in last lecture we discussed about operating systems in general, different features of operating systems. We talked about different modes like user mode and kernel mode, why operating system runs in kernel mode, why user applications run in user mode. We talked about different hardware as well. We talked about IO devices in general, how operating system handles them, how operating system uses device drivers to interact with these hardware devices and so on. Then at the end of the last lecture we also talked about Linux, since in this course we'll be aggressively using Linux, Ubuntu, for almost all the exercises for this course. So I have quickly given you an introduction, a brief overview of both the interfaces, CLI, command line interface, and GUI, graphical user interface of Ubuntu Linux. So I hope you have gone through that. We discussed very few basic commands in Linux, so that I assume were enough to start with this course. We are going to run many more commands, many more programs in this course, so I'll keep on explaining them throughout this course. If you have any questions, please drop me an email. I'm sure there are many resources available online for this course as well. For Linux, for C, we are going to use C language for programming most of our programs in this course, so there is a lot of help available online as well. So please feel free to go and search for online resources as well. There are very good videos on YouTube that are available for different topics in operating system as well, so try to have a look at those videos as well. So yeah, that's pretty much it. This is what we have done in the last lecture. We are going to start this lecture with operating system structures. So I'm gonna start this lecture with a diagram, since we are going to do a practical exercise in this lecture as well. So before going to the practical exercise, we need to set a very strong foundation of what we are going to implement today. So this is what we are going to talk. So in general, in today's lecture, what we're going to do is we're going to talk about what different operating system services are. We have already talked about different operating system kernels. We'll go into a little bit more detail of those modes as well. Then we'll talk about kernel modules, and finally we are going to do a kernel module exercise in Linux. We are going to develop our own kernel module. We'll test it and see how we can insert a kernel module, how to remove a kernel module. Now before we actually do that exercise, we need to understand what a kernel module is. So we need to set a foundation before we actually dive into the exercises. So this is what we're going to do today, and we are going to start with operating system services. Now as we discussed in the last lecture, that operating system is a resource allocator as well, a resource manager as well. An operating system does that using many services. Now in these slides we have not covered all the exercises all the services operating system does, but few of the major exercises. So I have actually split them into different sections so that you can actually understand what different services operating system can perform and where they actually fall. So this is a diagram of what operating system services architecture looks like. So we know at the bottom we have hardware devices, and for hardware to interact, or for operating system to interact with the hardware, it needs to interact with different device drivers, right? So operating system interacts with the device drivers, and device drivers interact with the hardware, and then operation is performed. Now with hardware as the bottom layer, and operating system being the topmost layer when it comes to hardware and operating system, then operating system has a portion for all the services that it provides. So those services there are many services obviously, and these are just some of the many services available over here. So for example, in order to interact with the file system, operating system uses a file system service. Similarly, in order to provide security and protection to user data, to user files and directory, operating system uses the protection and security service. In order to execute the programs, there is a separate service, we call it a program execution service as well. Then in order to communicate, for example, to check your emails, to connect to internet, to download files and so on, operating system uses communication services. Similarly, in order to detect some errors, in order to correct those errors, operating system uses error detection service and so on. And there are many other services available. Now, this is operating system's service section, and this is the hardware section. Now, in order for user to request operating system for some sort of interaction with the hardware, user has to request operating system that certain action to be performed. Now in that case, user will do that request, perform that request using the user interfaces. We talked about two user interfaces, and these are the major interfaces used in today's modern operating system. So there is a graphical user interface, there is a command line interface, there is a batch interface which is normally used in industry. We are not going there. This is normally used in manufacturing industry in general. So if, for example, as a user I want to print a page, what I'm gonna do is, for example, I have a Word file. What I will do is I will go to File, Print on my user interface and send a print command. So that print command will reach operating system. Now it will reach operating system. Where exactly does it go? It's very important. Operating system is very comprehensive, and when we talk about operating system, it's just a bunch of files. So where exactly that command goes, and what is actually the flow of that print command? So what happens is, as soon as I give the print command, there is a section called a system calls section, which takes that command. I'll talk about system calls in great detail in coming slides, but for now let's take it that this is a carrier, that it takes commands from any application from the user, in this case from Microsoft Word. It takes that command and it forwards that command to the services, operating system services, the concerned operating system service. So that concerned operating system service can be an IO operation. In this case, if you want to execute a program, it can be a program execution, but since we are printing a file and we are doing an IO operation, so that system call will be forwarded to operating system service called IO operation, and then IO operation knows that this is for printing, so IO operation will forward that request to hardware and your page will be printed. So this is just a very general view of how your operating system services work. How graphical user interface or a command line interface interacts with system call. System call is a very comprehensive topic, and this is what we're gonna do in most of the lecture today, and this is what we're gonna do in the exercise as well. So system calls is just a carrier. Please consider it as a carrier for now, and then that carrier transfers that request to operating system services, concerned operating system services, and then operating system services interact with the device drivers, and then device drivers perform that action. So this is how operating system services work, and this is exactly what I just told you. These are different services. This is just an explanation of this figure in the previous slide. So operating system does not have only these services, it has many more services. Now those services depend upon different operating systems also. Those services also depend upon which distribution of operating system you are using. For example, if you talk about Windows, then Windows Professional might have different services. Similarly, Microsoft Home users might have different services. Similarly, if you talk about Linux, Ubuntu might have different services, then CentOS might have different services, and similarly Fedora might have different services, and so on. But yes, some of the services which are very generic to operating system, they are available in almost all the operating system, like user interface service. It's available in almost all the modern operating systems, because we are going to interact with the operating system using any of the user interface. It can be a command line interface using terminal or shell, or it can be a graphical user interface using using GUI interface services. So these are some of the many services. Similarly, if we talk about some lesser known services to the user, but they are extremely important. One of them is a resource allocation service. Now resource allocation service is very important. We talked about resource allocation very briefly in last lecture. What happens normally is in resource allocation is, since operating system is in charge of doing everything in our computers, whether it's operating system own services or user applications, executing programs, cleaning up here and there, it's operating system's job. So when it comes to resource allocation, what happens is, now CPU is also a resource, right? It's a hardware. Hard drive is a hardware as well. Similarly, memory, RAM is hardware as well. So these are all resources which are managed by operating system. For example, if again let's take an example of printer. If two people want to print from a single printer, then the operating system, what it will do is it will let person 1 print first, and then person 2 will take person 2 will start printing. Now this is the responsibility of operating system to manage resources in this way. So if a resource is already busy, it will tell the entity that wants to use that resource that this resource is already busy, please wait. So this is what happens. So the jobs, for example in this case print jobs, they are in the queue. So whatever is coming, whatever job is next, once the first job is completed, that next job will start working, and then so on. So this is how resource allocation works. We are going to talk about resource allocation, especially process management and memory management, which falls in a broader category of resource allocation, in a lot more detail when we move to chapter number 3 and chapter number 4 and 5. They are all about process management and memory management, and they are very comprehensive chapters, and they are very interesting as well. How different researches are increasing the speed of our computers, how it is happening, why CPU speeds are increasing every day, but the size of the computer is still it's very compact. How this is happening, we are going to talk about all these things in coming lectures. And if you are looking for, not now, maybe this is your 3rd year, but if you are looking for a capstone project, this operating system can provide a good understanding of what capstone project you can take. So we are going to talk about that in coming lectures. So resource allocation, this is how resource allocation works. Now accounting can be managed on many different platforms, on many different domains. For example, if you are running a internet cafe and you want to know how much internet somebody has used for a certain amount of time, so that you can bill him, then accounting can be one of the services operating system can perform. Similarly, protection and security, we already talked about that. If there is a computer that has multiple users on it, similarly, let's take an example of an internet cafe. There is a computer that's being used by different users, and you don't know the users exactly because they can be random users not coming daily or so on. You need to make sure, your operating system needs to make sure that the environment is set accordingly, so that file of one of the users is not shared with another user. So these all things are done by operating system, and normally these things are done by operating system using operating system services. Now let's talk very quickly about operating system interfaces. Now operating system interface, as we talked in our last lecture as well, as a user we need something to interact with the operating system. Now that something can be a graphical user interface, it can be a command line interface. Now let's start with a command line interface because it gives you a lot of power as a user, and if you are a developer or a programmer, it gives you more freedom to interact with your operating system. So CLI is all about writing your commands. There is no mouse normally used in command line interfaces. You use your keyboard to provide commands, and whenever operating system starts, it starts with a shell flavor, with a flavor of command line interface, whatever you have chosen at the installation or whatever your system administrator has provided you. There are multiple types of command line interfaces, different types of shells available. C shell and Bond shell are two very famous shell commands available in Linux. So we are going to use Bond shell in this course. Now in CLI, what happens is whenever user provides a command, there are basically two steps what is going on in the background. So what happens is, if user wants to remove a file, if you remember we did this in in one of our exercises to remove a file. So there is a command called rm, and there is a file which we want to remove. So rm file.txt. rm is basically a program that is written separately, and it's waiting for it to be executed. So whenever operating system sees this command in terminal, it invokes this program, and this program takes a parameter file.txt and removes that. Right, this is the only thing that command is going to do. And once this is done, rm will return the control to operating system. If there is an error, then rm program will return an error to the user, to the operating system, and operating system will do whatever it wants to do with the error. For example, it might show that error to the user, it wants to log that error, it wants to send that error to a system administrator. So operating system, based on how it is programmed, will do whatever rm is going to return to the operating system. So basically these commands are actually programs that are sitting waiting for them to be executed based on some parameters provided to them, and then they perform actions. So this is what is happening with the copy command, this is what is happening with the move command, and this is what is happening with almost all the other commands which we ran in our last exercise, or whatever is available in Linux. So they are all programs, and they are waiting to be executed by getting some arguments, and then they perform actions accordingly. So this is what our CLI interface does. This is how it works, and this is how it looks like. So we already know how Linux terminal looks like, as we did an exercise in the previous class. This is a command prompt for Windows. This is how it looks like. Graphical user interface, we all know about graphical user interface. Modern computers, modern operating systems, they deal with graphical user interface. They provide an option for switching between a graphical user interface and command line interface. So graphical user interface, it uses many modern devices to help user interact with it. So it uses mouse, keyboards and monitors, touch devices, pointing devices as well, like writing pads and so on. So there are icons that we can double click and action will be performed. So this kind of interface was first invented by Xerox company. So it was then taken by Apple company. They created their first Macintosh using graphical user interface, and then Windows jumped in, and now we are all very used to this graphical user interface. As I mentioned earlier, modern operating systems, they provide option for both command line interfaces and graphical user interfaces. For Microsoft, we already know that we have a beautiful interface, and then we have MS-DOS command shell available. In Apple Mac OS, we use an Aqua GUI. Their GUI is called Aqua, and they have a terminal built into Mac OS X as well. Then in Unix and Linux, we already saw that they have graphical user interface. So these graphical user interface managers, there are many options that you can use. There is CDE, there is KDE, there is Genome, and obviously it gives you additional functionality through CLI as well. We have seen this in our previous exercise. This is how Windows desktop looks like. This is how Mac OS X looks like. This is how Ubuntu looks like. These are some of the examples of GUI. This is how Genome desktop looks like. So these are some of the many interfaces available. Then we have obviously smart devices. We're going to talk about some smart device operating systems as well, iOS and Android, in this lecture as well. So just to show you, I mean, we are already familiar with this. So these are some of the GUIs available for our touch devices. We use pointing device like our fingers to use these smart operating systems. Now this is how our GUI looks like. This is how our CLI looks like. Our next topic is very, very important, because it's going to set foundation for not only the coming exercises but coming topics as well. We need to understand how actually operating system interacts with user applications, and how then operating system interacts with the hardware. So what is happening in between? Until now we have seen that there are only two steps in general, if we see. So user requests something from operating system, and operating system interacts with the hardware and then provide results back to the user. So not only one user is interacting with printer, even I mean, one of the basics of operating system or our system is the processes. and the memories, they're always in use. They're always in use. So if user wants to read something from a file, the file is actually on disk, so user has to request operating system to interact with the disk, which is the hardware. So anything we want to do in computer is actually an interaction between a user and a hardware. And how to do that, we cannot provide control of the hardware to user, because if something goes wrong, hardware is very expensive and it can be disastrous. So we need a middle layer, a filter between a user and a hardware, and operating system is that filter that performs all the operations on behalf of the user. So how this is happening? It is happening through a system call. So what is a system call? System call basically is a programming interface to the services that operating system provides. So operating system provides services of interacting with the hardware. Operating system provides services of protection and security. It provides services for resource allocation, for accounting, and so on. Now fine, operating system services we already know, or operating system provide these services. Now how user programs interact with those services? Now user programs interact with those services using system calls, right? System calls are the middleman between. If you remember, we have seen this diagram that whenever a user program wants to interact with CPU, with operating system services, they have to go through these system calls, and these system calls are actually the ones that are going to be used as by a developer or a programmer to be accessed, so that their programs can be used, can use different features of a system or an operating system. So mostly, in order to interact with the system calls, we developers or programmers, we use an approach. We normally call that approach application programmer interface. So because system calls can be quite complex, they can be very complex. I mean, you need to interact with registers and so on through operating system. So system calls can be very complex, and sometimes operating system does not want to share that information of how a system call was implemented with a programmer or a developer, so that user programmers do not interact with the system calls to do something fishy, right? So the details of how system calls have been implemented, they are normally shadowed from the developers. So in order for developers to access those system calls, they are given a wrapper level of files. We normally call those files or that layer an API layer, application programming interface. I'm sure you have already gone through many APIs. For example, just to give you a quick example, for example, if you want to get weather of today from Yahoo server, what you're going to do is Yahoo is not going to give you access to its sensors directly, which are assessing the temperature. They are not going to give you a direct access to those sensors or the hardware. What they're going to do is they will provide you an API. So you will request the information from that API, and that API will return you the result. This is exactly what operating system is going to do. It will not give you direct access to system calls as a programmer. So what you're going to do is you are going to use application programming interface or APIs to access those system calls, because as I said, system calls, yes, you have direct access to system calls also. If you know how to access system calls as a programmer, excellent. I mean, you can do that, but sometimes they are very complex. So in order to hide the complexity of those system calls, programmers are provided with APIs so that programmers can use high level languages like C, C++ or Python to implement those calls. So these APIs are normally 3 types of APIs based on different operating systems. So in Windows, I'm sure you have already heard of Win32 API. I'm sure you know about that already. In Unix based systems, we normally use POSIX API or POSIX based system for POSIX based systems, which is Unix based systems normally. And then some of the operating systems, they also provide Java APIs for JVMs. Linux also provides Java APIs. I mean, you need to have JVM installed on your system, whatever system you are using, to access those APIs. For Windows APIs and POSIX APIs, they are by default part of the operating system, so that's why not a big deal. You don't have to worry about installing them. But yes, if you want to use some Java APIs, you need to make sure that JVM is installed on your system. So these are how you access system calls using APIs. Now let's get a quick example of what a system call might look like, right? So just to give you an idea of how a system call looks like in general, now this is a very basic pseudo code. It's not an actual code, just showing you an algorithm over here. This is how it works, and sometimes as an operating system you want to hide all these details from a programmer. You don't want to show programmer all these details, although this is still at a higher level. So some of the system calls might be very complicated, might be very sensitive, so the information of those system calls should not be shared with a developer or a programmer. I'm sure you might have heard of private APIs or private frameworks. These are something very similar to what I'm saying. So the information of these APIs or programs, they are hidden from the users because they are quite complicated, and these APIs these system calls and frameworks, they are very capable also. They can give access to the parts of the system that actually you should not know. For example, I mean, just to give you a quick example of how private frameworks or libraries work, if you are developing an app for iPhone or iPad or iOS, any application for any iOS, then you are required not to use any private API, any private frameworks from Apple. So there are some private frameworks also available. If you use that, then during the review process on the App Store, they are going to reject your app. So they don't want you to use that. They only want you to use the APIs they have provided you, right? Because those private frameworks are very capable, and obviously, I mean, Apple internal development is done using those private frameworks. So they don't want you to use that, although they are still available because they are being used by the developers of Apple themselves also. But for third-party developers, they provide APIs, normally called third-party APIs. They are provided to them also, besides providing them the generic APIs. So they want you to work on those frameworks or APIs instead of just directly communicating with the private frameworks or APIs. This is exactly what is happening over here for a system call. So this is a simple algorithm for copying the content of one file to another file. So this is my source file. So I want to copy the content within this file to a destination file. So what's going to happen is I need to get, so as an operating system I should know what is the name of the file, source file, what is the name of the destination file. By name I mean the path of the source file and the path of the destination file. So I need to know both of them. So this is what is happening. So if operating system is communicating with the user, what it's going to do is, for example, let's say we are on CLI or a command prompt. It will ask user enter the source file. So this line will say enter the source file. So user will enter the source file, so operating system will accept that. Similarly, same thing will happen with the output file as well, or destination file as well. So it will ask for the output file name or destination file name, accepts that file. Now what operating system gonna do is it will check for the file if they are available or not. If they are not available, then it will abort. Simply, it will abort. If they are there, then it will enter into a loop. It will start reading from the source file, keep on writing that thing on the destination file. When everything is done, when read fails or it reaches the end of the file, then it will close the output file, it will close the input file as well. Then it will write the message to the user saying that the file has been copied or so on, and it will terminate normally. If there are errors, it will display those errors to the user. So this is how a system call works in general, but there can be many complications behind it, right? So this is a very simple example. There might be complication of how to access the keyboard when taking input from the user, how to access the file on the disk when checking if it exists over there or not, how to read bytes and where to save them. So these complications, when we use APIs, they are normally hidden from users. So if I say this is an example of a high level API, it's not false, it's true. But yes, some of the system calls can be like this. They are very simple. you can use them. But normally now system calls are very complicated these days, because there is another layer of a wrapper file. We normally call them APIs, as we have just seen, and we use those APIs as a programmer to develop many things. This is how a system call looks like for copying a file content from the source file to the destination file. Similarly, let's take another example where we create a process, but in order to create a process we use an API. So as a developer, I want to create a process. That process can do anything. So in order to create a process, in order to create this process, what as a developer I'm going to do, I will use an API function called a create process function. This is a function used in Windows. So I will use this process. I will include whatever libraries are required. I'm sure you already know how programming languages work. For example, if I want to do a cout in C++ language, I have to include IOStream. If I want to do printf in C, I have to include stdio and so on. So I'm assuming that when a programmer is doing something like this, programmer is already including the required library. So in order to create a process, the programmer has already included the required libraries. Then the programmer's program makes a call to create process. Now that programmer needs to know only this, that's it. So whenever programmer calls this function internally automatically calls create process, which is a system call, which is a Windows system call. So programmer does not need to know this create process system call. Programmer only needs to know about the appropriate required API for creating a process. That's it. Underline this system call is made, which is create process, and a process is created, and programmer is being told somehow that the function the process is created, or an error message is shown to the programmer if there is an error in creating the process. This is a very simple 3-step process. In order to create a process, call an API function will automatically call the internal system call and show the response to the programmer. This is how it works. Now this is an example of a very simple read function. It's an API that has a read function inside it in Unix. So I want to read a file, for example, and in order to read a file I need to interact with the disk, I have to interact with the CPU, I have to tell how many bytes, I have to interact with the RAM as well. So all these complications of where exactly in the RAM should I go, where exactly on the disk should I go to read a file, these are complications have been hidden from the developer using the API, and this API is called a read API. This is how an API looks like. This is a part of this library, unistd.h. So this read function of Unix is available in this API. So what is happening, very simple. I'm sure you already know about how functions work. This is the return type. Whatever this function is going to return will be returned in this type of value. So this is the name of the function. It takes a file descriptor, it takes a buffer, reads the amount of bytes in this count, and keeps on pushing the characters into the buffer, and then whenever that information is read from the file, it's returned. So this is how an API looks like, and there are several APIs in Unix, Linux, even in Windows and Mac OS. There are so many available. So as a programmer or a developer, you don't have to worry about system calls. You don't have to interact with the system calls directly. No, you don't need that. You just have to call these APIs, and rest of the things will be done by the operating system itself. So this is what I told you. This is how the details, complex details of our system calls are actually hidden from the developer, and operating system manages everything. And this is just a graphical representation of what I said. For example, if user application wants to open a file, what it will do is it will use an open function, open API function, and that function will use a system call. That system call will do all the necessary things underneath it and return the results of that open function API call to the user application. It can be an error, it can be a message, it can be an actual file that will be returned by opening. So this is how it looks like. Obviously, I mean, user applications will run in user mode, and all the system calls will be working in the kernel mode mostly, because operating system is directly interacting with the hardware here. Now there are different types of system calls available. These are some of the many system calls available in modern operating systems. But yes, these are the general system calls available, which are used every day by developers and programmers. They are very, very comprehensive. I will provide details of some of them over here to tell you what each of these system calls headings they do. So these are just the headings of many services, and inside them they have so many of them available. So let's talk about them one by one. So if I talk about, so these are process control, file manipulation, and so on. So if I talk about process control over here, I've given an example over here of two of the operating systems. So in order to use an API in Windows for using the process control, in order to create a process, we have already seen that in Windows we use an API called create process. In Unix, this process is called a fork process. Similarly, if I want to exit that process, I'll use exit process in Windows and use exit function in Unix. Similarly, for manipulation of files, in Windows we use create file, in Unix we use open. Similarly, to write to a file, in Windows we use write file, and in Unix we use write, and so on. These are the APIs in both Windows and Unix for doing many of the things, and behind these things we have the system calls that are being developed for us. We don't have to worry about them. Let's talk a little bit more about our system calls and the type of system calls we have. So we already discussed that we have different types of system calls available, and we do have APIs to access them in order to make sure that we don't dive into a lot of complexity of the system calls. To start with, we have a process control system call that has multiple APIs available, and what it does is it helps us in creating processes, killing those processes or terminating those processes, loading those processes and executing those processes. Then it helps us in allocating and freeing memory by removing those processes from the memory. So all of these things are done by system calls of process control. So if we take an example of how it works in different operating systems, let's start with MS-DOS. What happens in process control system call is, now MS-DOS is a single tasking operating system or single tasking program. What it does is, whenever a system boots, this is how the structure of MS-DOS looks like. So it has a kernel, it has a command interpreter, and it has free memories. So kernel contains some necessary files to load up your system. Command interpreter, what it does is, whatever command we write, it interprets it and performs actions accordingly. So for example, if we run a program in MS-DOS, what happens is, this is how the structure of a program and overall MS-DOS operating system looks like. So it will still have that kernel, it will still have that command interpreter, and that free space will be allocated to the process as much as that process requires. Now if another process comes, this process has to exit this space so that next process can come and that can run. That's why MS-DOS runs only a single task at a time, only a single process at a time. However, when we talk about Unix based systems, we normally call them FreeBSD also. BSD is Barclay's software distribution. You can read about it online. So in Unix based system, what happens is, Unix based systems are normally multitasking even when they are running in CLI command prompt. What it does is, it can run multiple processes at the same time, and depending upon the process and how processes being allocated to these processes, it's a broader topic that we're going to talk about in process management and CPU scheduling. And now how these processes can be divided into multiple processes, we will talk about that in coming lectures as well, and we are going to write some programs in for creating processes and creating parent and child processes and so on. So this is actually the default structure of the FreeBSD or Unix based systems looks like. So whenever there is a process, it comes over here. If another process wants to execute, it comes over here as well. If another process comes, it can still be accommodated as long as we have enough free space available. When our processes, when they are done, they return a code of 0 to the operating system, telling operating system that we are done, we don't need any more space, we don't need any more CPU. If however there is an error in a process, that error can be anything. For example, a process was looking for an IO device and it was not available, it will return something, a number greater than 0, so that operating system would know that okay, there is an error. So and operating system can handle those errors based on what kind of error it was. So this is how process controls are managed in MS-DOS single tasking operating systems and FreeBSDs or Unix based systems which are multitasking. Then we have file management. We discussed about this already, that file management is about creating files and directories, deleting them, reading and writing them, moving them, copying them, closing them. Actually, we did an exercise on CLI as well, where we used most of these commands to perform some operations. So when we were removing a file or a directory from CLI, we were actually using an RM, which we already discussed at the start of this this course, that we were using actually the RM program that was actually calling the system calls underneath, and operating system was performing operation based on those system calls. So file management does all these things. Then we have device management. Whenever user is requesting a resource, that request goes to operating system based on the system calls, and operating system looks to see if that resource is available. If that resource is available, operating system allocates that resource to that program. If it's not available, it will send a message through the system call to that program that this resource is currently not available. You have to wait to get this resource. And similarly, we can read and write and reposition these managements, and all these things they fall under the category of device management. Then information maintenance. Information maintenance is actually monitoring and maintenance of the whole system. System administrators use this category a lot because they want to get to know how many users are there, what is the current time or date, what is the quota for each user, for how long a user was logged in, for how long a user is using the internet, what is the memory dump, how to get that, how to remove that, how to free some space, getting operating system version, getting software version. So system administrators, I mean, their whole day it goes in monitoring stuff, different stuff. So in order to do that, they already have some built-in software. Sometimes they might have to write their own scripts or software to get this information. So all of this information, it falls under the category of information maintenance. Then we have communication, as we discussed earlier. If you want to connect to internet, if you want to open a connection, close a connection, open a session, close a session, need to get a process ID, need to read a message, download a file, then it falls all in the system calls communication category. And we have different APIs for that, as we have already seen. Finally, we have protection. Protection is all about protecting user files, user data, or system in general, allowing a user to use a certain file or a folder, denying user, not allowing user to use that file. Similarly, not only at the user level but at the group level. So if somebody is a part of a group, for example, a system administrator has assigned a group to teachers and assigned a group to students, then students can access a certain folder at a particular time, although teachers have access to that folder all the time. So these all things fall under the category of protection, and system calls for that do a lot of things underneath. For example, assigning the permissions, getting the permissions, and how to assign the permissions, how not to assign the permission. However, APIs help us only to deal with few of the informations, not to deal with all the complications of the system calls of protection. Now comes our system programs. What system programs they do normally is these system programs, we actually talked about operating system. That operating system is just a collection of bunch of files along with some applications and programs. Those applications and programs, they come as a bundle with operating system. For example, if we talk about Windows, and Task Manager is one of the programs that comes built in with Windows. Similarly, Notepad comes as a built-in program for editing different text files. So these are the programs that are part of the operating system. They can perform many things for you. They can be different services that can run, and they can be file manipulation systems as well. For example, in Mac OS, there is an application called Disk Utility application. It comes built in with Mac OS X, that can be used for formatting and partitioning hard drives. Similarly, for Linux, terminal comes built in. You can do, it's very powerful. It can do a lot of things for you. It can create services, delete services, and we have already seen how powerful it is. We have done exercises on that as well. So system programs are actually part of the operating system, or at least the programs that actually help operating system perform certain actions. So they are considered the part of the bundle, overall bundle that comes with operating system. Now they can, as I told you, they can do many things, and they can be used for checking information, status information, creating files, deleting files, file modifications as well, for checking support. For example, Linux comes with a built-in support for C and C++ compilers. You don't have to install them. Similarly, many other programs that are required, that provide help in creating many other programs, they are also part of the operating system, and these are called system programs as well. Then we have application programs. Then application programs are not actually operating system programs. They don't belong to the system themselves. They are actually run by the user. They are user programs that are run by the user, and operating system perform actions on behalf of these programs. For example, Microsoft Word is not a part of Windows operating system. It comes as a separate install, so you have to install that. It can still access many of the operating system provided things like printer and different system fonts it can access, but obviously it can do that only by getting permissions from the operating system. Now these application programs can be launched through command line. We have already seen how to launch Firefox from CLI. We did that exercise in the last class. And these application programs, obviously they can be accessed using mouse click. We can double click a program and it can launch, and on our smart devices we can touch those program icons to launch them. Then we have operating system structures. These operating system structures are the way of telling how an operating system has been structured, or what is the architecture of an operating system for a particular operating system. Now there are many structures available. Some of the operating systems, they follow one of these structures. Some of them, they follow multiple of these structures. So let's start talking about what these operating system structures are, what different operating system use different operating system structures. So let's start with the simple structure. Microsoft DOS, MS-DOS, it uses simple structure. It's very simple. It's a simple tasking operating system. It does not run multiple tasks at the same time, and it has a very simple, just because of this reason, it has a very simple architecture. It doesn't have multiple modules. It has a simple way of handling things, as I showed you in the example as well. It has free space. It will load a program in that. When that program is done, another program can load into that. It will have a command interpreter over there. It has kernels over there. So very, very simple structure it has. It doesn't have a very complicated structure. So that's why this structure from MS-DOS is called a simple structure. Then we have a layered structure. In layered structure, what happens is we have multiple layers of this structure, of this architecture. So the bottom layer is the hardware layer. Then we have multiple layers on top of that, and the topmost layer is the user interface layer. So what is happening over here, and one of the most important things of this layer structure is the layers can only talk to their subsequent layers. For example, layer 1 can talk to layer 0 only, layer 1 can talk to layer 2 as well. Layer 2, for example, can talk to layer n as well. So if layer n wants to talk to hardware, it cannot directly talk to the hardware. It has to talk to, for example, layer 2, and layer 2 has to talk to layer 1, layer 1 has to talk to layer 0, and so on. So these layers cannot talk to or jump from one layer to another layer. They can only talk to subsequent layers. Then we have a microkernel structure. This is a very famous structure that helps in keeping the kernel lightweight. What happens in this structure is a lot of information from the kernel is taken into user space. So not all the information is loaded into the kernel, only very necessary or ultimately necessary information is provided to the kernel, and the rest of the things, they are moved to user space. Now what is the benefit of that? One benefit is kernel becomes very lightweight. So kernel is not complex at all. It loads up, it boots up very quickly, and it's easier to understand. It's very easy to manage. Then it's more reliable and more secure, of course, because there are less things in the kernel. So obviously it's better. It's easier to secure that information. It's more reliable. If there is an error, it can be easily caught. Now if you see the diagram, this is how it looks like. What happens is we have, as always, a layer of hardware. And then we have a kernel mode, we have a user mode. In kernel mode, we only keep ultimately necessary things without which operating system cannot work. So for example, CPU scheduling services, then we have memory management, inter-process communication. Only these things are available in the kernel. Rest of the other things, they are just moved to the user mode. So all the application programs, even the file systems which were part of in other architecture, they are part of the kernel mode. Device drivers are also part of the kernel mode. They are just moved out of the kernel mode. So whenever they are required, they are called. So if device drivers are called anywhere, anytime, they are just called by the operating system. Information is taken from these device drivers, and then information is fed to the hardware accordingly. Now the only problem with this micro kernel structure is it becomes very slow when these modules which are in the user mode, they want to communicate with each other. For example, file systems, they want to talk to device drivers. They have to talk to device drivers through kernel mode. Similarly, if operating system wants to access hardware, it needs to get this information from device driver. So it has to go to device driver, get that information, and then interact with the hardware. So in case of inter-process communication happening over here on the user mode, or happening between kernel mode and user mode, this performance becomes very, very slow. Although the overall performance, if kernel mode processes are communicating with each other, becomes very fast, because they can still communicate with each other. But if there is a communication between kernel mode and user mode processes, it becomes pretty slow. The next one is the modules. This is pretty famous as well. Most of the recent operating systems or modern operating systems like Linux and Solaris, they use this approach. So what happens over here is kernel is allowed to load and unload the modules from it. So in order to make sure that kernel is not heavily bombarded with a lot of information and make it very complex, only few of the information is provided to the kernel, but again it can be loaded with more information, unlike microkernel structure where this information will stay in the user mode. But in the modules, what happens is if some information is required, it will be loaded in the kernel. This is what we're going to do today. We are going to create our own kernel module, and we will load that kernel module into the kernel. Then we perform some operation on that using that module on the kernel. Then we remove that kernel when not required. So this is how modules work. Whenever they are required, they can be loaded into the kernel. When they are not required, they can be removed from the kernel. For example, if I have a joystick to be attached to my computer, so I want to use that joystick, and there is no kernel module or no kernel driver available in the kernel, I can load that kernel driver into my kernel module when required, and whenever it is not required, whenever it is not attached, can be removed from the kernel modules. So this is how modern operating systems normally work, especially Linux and Solaris. And this is how it looks like whenever some of the kernel modules are already loaded into the kernel, and if more kernel modules are required, we can still load those kernel modules into the kernel. Then we have a hybrid approach for operating system structures. Mac OS X, for example, it uses a very complicated operating system structure. It uses the combination of multiple structure. It doesn't use a single structure. So this is how it looks like. It has an Aqua at the top, which is the graphical user interface for Mac OS X. Then it uses some special application environment services like Java. For Java, they use this. For Cocoa, their own built-in libraries for that. QuickTime for audio and video, they use that, and they use Linux BSD, Unix based services as well that are in BSD. So BSD then goes to the kernel environment, and there are some of the kernel environment BSDs that run over here. Then they have their own mash kernel environment also that runs over here. At the bottom they have IO kit to interact with the hardware. Then they have kernel extensions. If you want to still add some more extensions to the kernel, that can be added. So a very complex structure is being used by Mac OS X, and why they are able to successfully build this structure and run this structure is because they build their own hardware. So they are not porting their operating system on a separate hardware. They have their own hardware architecture. On top of that hardware architecture, they are just loading their operating system. So if that operating system is loaded on a different architecture, some extra work is needed. But in this case, they are happy to do that because they are building their own hardware, they have their own software, so they know how to interact with their libraries, know how to interact with the hardware, and they don't have to worry about loading different libraries that come from Cocoa or so on, which is their built-in services. Then iOS is actually very similar to Mac OS X. It's just a subset of that. It uses not all the services obviously, but it can run on different CPU architecture. Well, Mac OS X can still run on different architectures as well, but it cannot run on different other very different architecture, hardware architecture like Windows or so on. So iOS only runs on Apple devices, and it's pretty similar to what Mac OS X does. It's just a subset of that. Use core services and core OS, and then on top of that they use their own framework of Cocoa Touch, that is for touch devices instead of using the pointing devices. Then Android also use something similar, but it alliances with different hardware vendors as well. So Samsung, they have their own set of Android operating system that they launch. Similarly, Google, they have for Nexus and so on, they have their own set of operating system, although the base operating system remains the same, but they keep on changing few things here and there just to make sure that they are compatible with their hardware. And this is how Android works. They have their own runtime that is part of almost all the Android operating system. Then they have some libraries. These libraries might be different depending upon the hardware. However, some of the libraries like SQLite, they'll be part of almost all the operating systems. Then there is WebKit, which is part of almost all the operating system for accessing the web and so on. Then as developers, we use application framework that is used to access these libraries, these system calls. So we use these APIs as developer to access them and perform different actions on the hardware. Alright, that's it for the theoretical part of today's lecture. What we're going to do now is we are going to create a kernel module, and we will load that kernel module into kernel, Linux kernel, then perform some action on it, and then we are going to just unload that module. Now how it happens is, this is the flow of the overall process. So we write a kernel module. I'm going to write that kernel module in C language, because kernel modules are normally written in C language. So I'm going to write a kernel module, very simple one, hello world type of kernel module I'm going to write. Now this kernel module then uses an API, module underscore init API, to be loaded into the Linux kernel. This API helps us in loading, and we don't have to worry about all the complex structure behind registering this module. We don't have to do that. This module will load it into the kernel, it will register it with the kernel, and we don't have to worry about it. So, and we just display some message on the kernel, and after that we'll just unload that or unregister that module using module underscore exit API, and we don't have to worry about how system is doing that. We don't have to worry about the system calls behind it. This module will automatically call this API will automatically call all the required system calls and unload our module from the register from the Linux kernel. So this is what we're gonna do. I'm gonna do that in Ubuntu, but you can do it in any Linux distribution you like. And this is how this exercise looks like. Exercise number 1 was a CLI exercise we did, and this is what we're going to do. So we are going to create a kernel module in C language that just displays a greeting message, hello world or anything. We have to make sure that all the appropriate libraries are included in the program, and once we are done with this program, we'll just unload that kernel from the kernel module.